So I'm going to spend quite a bit of time going through, maybe the amortization on the maintenance and recurring, mainly non-engineering costs on deployed estate, changing regime tariffs and future buys for power, particularly when focused on public cloud. I'm kind of estimating on not overrunning by more than 20 or 25 minutes, and the deep dive on offsetting the depreciation of the tax liabilities in different geographies. I'm joking, okay. But it does maybe raise an important point here, and one that I'll be keen to tell quite a few large AI companies about when I set up an independent consultancy for this kind of thing, that we as service providers, or you as service providers, for cloud or cloud in enterprise, you kind of exist on that margin of the total cost of ownership, charging less for the service that you provide than the money that you take in. And that might be an old style business metric for the world of large language models in particular, but it's our bread and butter. And I mean that as a silicon person. Great. So let's restart. Going to introduce myself. I come from Ampere Computing. I've been with them for about four and a bit years now. Before that, long time in Intel. I've spent time on AI product management. I've spent time on data center security and high-speed message focus. And before that, for the Brits among us, or the English among us, I was building your NHS converged healthcare system and spending about 12 billion of your pounds on that. Not all of which I was responsible for at the time. I've brought along with me Clippy. Clippy is Clippy Pete is my alter ego. So there's kind of a couple of reasons for that. Clippy Pete, or Clippy, back in the day, was genuinely helpful. And my role within Ampere is Europe focused. I am technical pre-sales. And I generally just want to be helpful, just like the old Clippy. He might not have delivered much. And I'm not promising anything more. But Clippy is also memeing, is also becoming popular as a kind of a way of expressing us as individual engineers and actors within the tech industry and consumers within the tech industry to reclaim the products that we should own, to be able to configure and own those products through time without onerous licensing conditions, without X and Y features suddenly being withdrawn, and with the ability to repair our own stuff. And that's what the Clippy meme is also about. I think it's a really good parallel for the CloudStack community. We're going to talk about some TCO. We're going to talk about how you can repatriate onto a different architecture, because we are not Intel and AMD. But after having introduced myself, I'll go through Ampere itself, and who in the room has come across Ampere as a company. 1, 2, 3, 4, 5. Excellent. I've got some virgins to practice on. So we are a silicon design company. And what does that mean? So we take a set of requirements for silicon chips. We translate that into architecture and we have that manufactured, and then we work with partners like a HPE, like a Supermicro or a Gigabyte or even ASRock for boards, and have compute platforms built. So we're a particular flavor of HPE ProLiant. They have Ampere chips like ProLiant has AMD and Intel chips. And the same goes for many, many others. We are 6-7 years old. We're formed from some acquisitions, but also from a bunch of folks that were in primarily Intel. Our founder is Renee James. She left Intel to kind of retire, but she's not quite the kind of woman to just retire. She went then and formed, with some venture capital money, Ampere as a company, and brought in ARM server chip technology. We've since then developed that and gone through several generations of chip. We have Ampere Ultra and Ultra Max in market. Ampere 1 is our new chip, and Ampere 1M is coming through right now with a higher memory capability, higher number of memory channels. We are focused on cloud or cloud adjacent use cases. So that might be workstations, or that might be delivering cloud at the edge, or networking and telco capabilities at the edge in some embedded form factors. But we're quite monk-like, we're quite disciplined in order to deliver, firstly, power efficiency. We've got to always be air-cooled, single-threaded, lots of private resources per core. So it's kind of a socialist concept that every core is equal. And as cloud service providers yourself, or as enterprises that have services like cloud, you'll be painfully aware that turbo boosting some chips are at some part of the actual die of the chip means that somebody else who's got virtual instances on the other side of the chip is suddenly being given, fewer resources, a lower clock speed, lower access to things like memory bandwidth. We're very open about giving cores, and many cores, lots of access to chips. And we'll put the right number of accelerators on there, and certainly the right number of and the right types of security, intellectual property blocks and features. So that looks like a set of graphs by which you can describe, and I'm going to go wider than Ampere here, cloud native features in silicon. And all of your customers are going to want latencies that are super predictable. So when a web transaction, maybe you're using PHP and Magento as a framework for online shopping provision. When those transactions go through, when that catalog image needs to be delivered, it needs to be the same every time. Because certainly for online shopping, those latencies, as we're going to hear from Ido later on, hello, those latencies, they need to be understood and expected by your customers, and that's going to lead to greater retention in shopping, or greater, back-end delivery of API requests when you're providing mobile app server We deliver a large number of cores. All of those cores can work at top frequency all of the time. So if the workload is there, every one of now 192 cores can work at 3.2 gigahertz and will do that all day long. We design and put, and TSMC prints a lot of transistors into our dies, about 100 billion. Can't afford to turn them all on all of the time, but we want you to use as many of those transistors at their stated frequency as much of the time as possible. So we work to understand our thermal budgets and work with the ecosystem of software, from compilers up to Nginx, so that we can have their software use as much of our processor as efficiently as possible all of the time. And it leads to this very dependable delivery of workload as opposed to going up and down with thermal scaling. Along with that ethos of wanting to use all the transistors all of the time, getting rid of the hyperthreading just means that we want you to see those electrical, those sums per watt energy efficiencies at much higher utilization. Think more in terms of 80–90% utilization. So what are we doing to deliver that? So nested virtualization. Virtualization will give you 20% utilization across your estate. It's crap, but that was the 1990s. Nested virtualization, if you're not already using containerization, it's virtual machines within virtual machines. It's just like Terry Pratchett, it's turtles all the way down. In order to give a lot of cores, a lot of equal access to resources, we're very keen on both quality of service enforcement for providing applications and particular virtual machines, access to memory bandwidth, access to certain policies within cache, to be able to deliver application performance in more predictability. So both quality of service and enforcement and adaptive traffic management across a whole network of cores is super important. Vito.
Yeah, Pete, I have a question about this. So you say 20% utilization of CPUs, a number you see on general virtualization.
Absolutely, yeah.
What I see as a service provider is that we are usually constrained on memory in a box, because the CloudStack has allocated all the memory to the machines, and then CPUs are then idle. For most of the time they are idle. At certain peak hours they peak, but then the rest of the time the CPUs are just idle.
Yeah. Great minds think alike. Couple of slides over,
okay,
and we're there.
And then the one remark, then you need to buy the bigger CPUs to get more memory connected, because the lower end CPUs do not allow you to add 2 terabytes memory, for example.
Yeah. And suddenly you're on the good Friday, sort of Friday morning, not Friday afternoon silicon from TSMC, and that costs. So all of that chip architecture has to mean some end result for customers, for buyers, for customers as well. And one of the points I really wanted to bring out was that, and I'm preaching to the converted here, moving workloads off hyperscalers. And I don't know, is anybody aware of Marco Cinarelli's work on the total cost of ownership of moving off of AWS, Azure, and GCP? So Marco works at Shape Blue, and about a year and a half ago maybe, he came out with a total cost of ownership modeling tool for bringing your workloads off of a hyperscaler with operational costs that just accrue in very straight lines, and then moving that on-premise or onto colo, wherever you guys and girls decide to put it. And so, you know, he came up with this. I've shamelessly copied that graph and corrected one or two mistakes in the spreadsheet, but we'll have a word about that later. And we come down to this, where you start more expensive because you've got capital outlay, okay? And feel free to quibble with me. I am showing you a reality, depending on who you are as a company. You may have credits that keep you low down, but with the hyperscalers, it's still going to grow. And you cannot stop that onward growth. We've got cost control when we have things on premise, and when we can work with and employ engineers that are invested in their own delivery and can take pride in their own delivery, as opposed to, you know, an AWS qualified engineer in central London, bang, because it was £5 an hour more lucrative on the next job, and then 6 months again, change. So fully credit Marco Cinerelli. This is an open tool, and I've scaled this for 2,000 instances. That was just a finger in the air there. But these two lines at the bottom with x86 and ARM64 are showing you basically incremental operational costs versus an initial investment and then getting returns on the investment. Focusing down in the bottom, this is the extra saving that is possible by converting onto ARM64. And the reasoning for that is because we operate at a lower power for the CPU to be able to deliver the same number of sums, the same number of calculations, the same number of API transactions, website page deliveries, whatever. That then translates down to lower fans. So we're running servers at a lower power, maybe 40% lower for the same workload. That then means you can fill your racks up a bit more because you're not busting the power budget on your rack. You're becoming more dense, okay? And in here, you know, we start to see, depending on whether you're private cores for your customers or whether you're kind of vCPUs, virtualized shared cores for your customer, the ability to start to overcommit to a greater extent. So the overcommit on the compute resources for cloud native, you know, single-threaded, equal resources per core types of processors, means that you can drive that compute overcommit up into hopefully the 80%, get maybe even up to a 4.5 overcommit ratio, such that your memory bandwidth becomes that limitation. In order to do this, so we're continuing some of the why. In order to do this, you know, we have concentrated on particular types of workload. I call it the 80% of normal compute that the world just keeps on getting on with. We don't concentrate particularly on HPC. We're good for some HPC use cases, but that's not our raison d'etre. We also don't concentrate in any way, actually, on AI, you know, generative model training. And so bread and butter workflow would be Nginx, Redis, Memcached database, And then quite a lot of traditional AI inference. So everything from random walk and through convolutions to whisper translation and DLRM, so recommendation engine type workloads. So in eschewing one set of workloads, we're able to appeal with energy efficiency to the 80% of workloads that we all just get on with day to day and runs the world. We are at ARM64. That's a different instruction set for those who are in the top level of software world. Being a different instruction set, you need a different executable. So you need to port those executables. Now, the world's been at this for a long time. There's been an ARM architecture for 40 years. It started over in Cambridge with a couple of folks coming out of the BBC microcomputer, and off of the back of the work that had been done for Acorn and the BBC, ARM was born out of that. So there is a set of software that's been there forever. Android gaming in the cloud just runs natively on us. You just don't have to think about it. But that porting's required. There's two types. There's to run on Ampere or another ARM processor. It's called light because it just works. We have Graviton in AWS, Axiom in GCP, and we have Cobalt in Azure as the ARM processors there. Sneaky little thing here, those ARM workloads, which generally the hyperscalers can afford to charge less for, they kind of use that as a sort of a vendor lock-in because there's nowhere else to go outside. Well, there is. It's Ampere. So, use Ampere. I should stop being so biased here. Use Ampere with its basic binary compatibility because it's one of the lower effort ways of landing the kind of workloads where you're trying to get people, your prospective customers, moved off of a hyperscaler because they're already using their ARM services. That's not an argument anymore. Porting heavy, x86 to ARM64. Like there's a CloudStack community, there's a community of ARM silicon providers for a number of years now, probably more than a decade. We've had the ability to go in and inspect source code. So there's the Ampere Porting Advisor that we forked, and what we use that for is to help our customers and platform providers go into any of their, Python, Java, Go, C, C++, Fortran. I thought I'd dig out an icon of a greybeard there. But I do like the fact that Fortran's in there. I don't expect a lot of sales from it. And that's a Docker image, Python script, an executable, depends how you want to use it, that's going to go through your repo and look for dependencies, look for the types of code patterns that we know are indicative of being dependent on x86 instructions and incompatibilities. Quite often, you're going to get arguments from prospective customers, the purchasers, that, I can't move all my development onto this. Well, half of the time, the development has moved onto ARM already. They're on Apple M something, and they're having to cross-compile over to x86 to get the x86 cloud images out there. So, time to reference Lucien here. Thanks to Lucien, and probably did Rohit do some work on this? Pearl's done some work on this as well. Yeah. So we've worked with the CloudStack community. We've worked with Shape Blue on a joint architecture, on a plan to allow CloudStack existing customers and prospective customers to port over and use Ampere and ARM ecosystem platforms, whether it's 19-inch rack mount or workstation, whatever. Refreshingly, it's all pretty normal. Very little to see here, move on. The ARM ecosystem has grown up. It's very adult. It starts with firmware, UFEI BIOS, BMC, Redfish, IPMI, and I'm just listing things here now. All of that is normal. That's a program that's been undertaken by numerous companies to make seamless transitions to a different architecture. It'll probably happen for RISC-V as well, but we'll come to that. But it's refreshingly normal when you look at the type of architecture that is inherent with CloudStack. You know, so we're both in management and instance servers. We can split with zones, pods, racks, clusters, form primary and secondary storage. There are a couple of differences, and they're not massively intelligent differences. No compilation necessary. You need an ARM OS to run this on, so an Ubuntu, a Debian, maybe an OpenBSD. Do you guys run on that? Goes without saying. There's a different system VM template, or a different set of system VM templates. So look for ARM Architecture 64. And there's a number of those to choose. KVM's a great place to start when it comes to the hypervisor. Acceleration of that, it's already in Neon. Neon is the ARM instruction set that encompasses a lot of things. Part of that is an equivalent of the Intel VT and VT extensions. And then a few little details on telemetry, frequency management. Vito, to your point, overcommit headroom. You know, we see our existing European customers providing vCPUs at up to 4.5 times overcommit on compute, so that they can just max out that memory bandwidth. I've left a little bit of time for questions. If you want to contact Clippy Pete, he is at the end of this QR code. And I've got a couple of URLs. The first one is that joint architecture. It's refreshingly like a normal install routine for any CloudStack implementation. And we also provide some resources at Ampere for developers and also for DevOps as well. Thank you very much for your ears.
There's a question.
Any questions, Craig?
I have one question. The graph which you showed a couple of slides back.
Yeah.
Does that include the cost of porting also?
So, question was cost of porting included in the graph. So that non-recurring engineering, no, it doesn't include that. So yeah, there's complications like, you know, AWS cloud credits, a desperate salesman near the end of the quarter, non-recurring engineering for software changes. One of the things that we do on the website is just track a whole plethora of software, of containerization, and then all the way down to different firmwares, which you can build yourself for Ampere and ARM platforms. And everything in the middle, applications, Nginx, languages, Go, you name it, the works. Yeah, so we're not just about throwing silicon over the wall and expecting people to use it. You got to, if you're something new in the industry, you've got to take and build a community with you. Vito.
You mentioned that you work with, for example, Supermicro and other vendors. Everybody here is probably used to go to Dell, Supermicro, HP, just buy a box and say, put an EPYC in there, an Intel in there, and just get me a box. Does it work the same with Ampere? Do I simply go to a supplier, say, I want a box, give me CPU memory, and they ship it? How is it that easy?
Pretty much, yeah. So we work with HPE. HPE's on the Ultra silicon. We're now on Ampere 1. So, I don't know, Ultra maybe had 10, 15 vendors of all sorts of different flavors. Some of them are like the Foxcons and the WeWins of the world. Ampere 1, we're probably on 7 vendors now. And then Ampere 1M, we'll add another 2, 3 vendors. Yeah. Does that answer your question?
Well, I'll probably just need to go to the catalog online and just see, okay, I want to buy this box and give it a try.
Yeah.
Yeah, it's that easy.
Yeah, so the solutions area of the website.
Yeah, we have a whereby we go on our blog website.
Okay, great.
Which was to direct links.
The performance comparison between the Intel, the 64-bit AMD and Ampere, were there any security patches enabled on the chips, like against Spectre, Meltdown?
So we're kind of developed in the world that was dealing with Spectre and Meltdown. So we don't have any CVEs open against Spectre and Meltdown.
Yeah, I know.
Yeah.
I asked the wrong way.
Yeah.
The x64 chips, were they Spectre Meltdown disabled or enabled compared to yours?
I see what you mean. No, so we're using vanilla.
Okay.
Yeah, the question was, is the performance kind of fair between x86? Are we deliberately hobbling x86 by, making it run in single-threaded mode and maybe limiting some of the thermals and of course, applying changes for older Xeons for Spectre and Meltdown? No, we're pretty vanilla about that. I haven't included all of the small print, but in a normal presentation that we give, there's usually about 4 or 5 pages of small print, how we run our benchmarks, how you can recreate those benchmarks.
Because in the usual data center, of course, we'll patch all that stuff.
Yeah. I mean, we're public about this stuff. So spec int rate 2017 is that's run by not us. Don't trust us. Go and have a look at the 30 megabytes of computers that have been through the tests.
Great, thank you very much.
Thank you.